How does a plane designed in garages end up fighting for its life above South Los Angeles on an ordinary January day? At Compton's busy airfield, tail number N8.3S became a cipher of what can go wrong when speed, skill, and design margins collide. Few outside the home-built community know the Quickie Q-2's quirks, until the runway goes quiet and the sirens begin. This is not just a crash, it's a case study in the razor-thin line between performance and peril. What happened in those final seconds? And what does it reveal about the risks we accept in the name of freedom to fly? The answers lead into a world of brilliant engineering, stubborn physics, and choices measured in feet and seconds. Follow the trail of clues from the wreckage to the rulebook to understand why N813S never got a second chance. On January 21, 2000, the rhythms of a clear winter day at Compton Woodley Airport felt familiar. A parade of trainers circled the pattern over homes and storefronts, their radio calls crackling on a common frequency in the absence of a tower. Just a few miles away, the wide-body lanes of Los Angeles International traced their arcs across the sky. The big jets high and fast under the Class B umbrella, while down low, Compton's shorter runways accommodated weekend pilots and working instructors who knew every chimney on downwind. Into this scene rolled a compact, low-slung composite with a distinctive silhouette, a Quickie Q-2, registered N813S, the product not of a factory line, but of a garage and a builder's hands. The pilot was launching on a private flight that should have been routine, the kind of short hop that begins with a walk-around and ends with a tie-down and a story about a smooth landing. The pre-flight choreography looked standard. Canopy latched, fuel checked, control surfaces moved and watched, the small propeller hand-positioned before the starter engaged. On the taxiways, N813S sat low, its stance a reminder that this airplane's main wheels lived at the tips of its forward-lifting surface. A brief engine run-up at the hold short line, a glance for traffic, a radio call onto the common frequency, and then the Quickie pointed its nose into a sliver of asphalt that demands discipline, runways that leave little room for hesitation and none for miscalculation. Witnesses on the field recall the takeoff roll as bright and quick, the sound of the engine crisp against the hum of the city. What happened next unfolded close to the runway in that tight envelope where acceleration becomes flight and small deviations gather momentum. Within minutes of brake release, the flight was over. Sirens approached, the pattern traffic widened to give room, and a circle of professionals and bystanders converged at the edge of the pavement. In the immediate aftermath, the questions were practical, almost clinical. Was there a fire? Did anyone else see what happened? Could the aircraft be made safe for responders? But as the scene settled and the paperwork began, the questions turned more pointed. N803S was not another Cessna or Piper, and that fact mattered as investigators began to log the marks in the turf and the scuffs on the composite skin. The Quickie Q-2 is a home-built kit plane with a reputation, compact, efficient, and demanding of precise handling near the ground. Its exotic lines, celebrated in builder magazines, are not cosmetic. They signal different aerodynamic rules and different habits required of the pilot sitting 2 feet above the asphalt. At an airport like Compton, where the runway length focuses the mind and the traffic density forces tight timing, the margins for a specialty aircraft narrow further, especially during takeoff and landing, when control inputs and airspeed discipline must be exact. The benign weather that afternoon offered no easy scapegoat. The hard questions, then, were about fit. The fit between airplane and environment, between a pilot's proficiency and an airplane's idiosyncrasies, and between the freedoms embedded in the experimental category and the guardrails that keep that freedom from turning punitive. By nightfall, pieces were measured and cataloged, and the paper trail began to grow. Registration data confirming the experimental status, notes on modifications, if any, a confirmation of the local conditions, and preliminary accounts from those who watched the brief flight begin and end beneath the LAX arrival corridors. Families were notified, and the community at Compton, mechanics, instructors, hangar neighbors, did what aviation communities do after a loss. They compared notes, they debated respectfully, and they asked how this could have gone differently. In those conversations, one theme surfaced again and again: to understand how a promising takeoff at an urban airfield could end in ruin within the airport fence. You have to start with the machine itself and the particular demands it makes on those who fly it. Before the why, there is the what. The Quickie Q-2's tandem wing design, its razor-thin low-speed margins, and its sensitivities on the ground. The Quickie Q-2 does not look like a conventional airplane because it isn't. Its tandem wing layout, one lifting surface in front, another behind, rearranges basic assumptions about how an aircraft takes off, lands, and behaves near the margins. In a typical airplane, a large main wing bears most of the load and a tail balances it. In the Q-2, the forward wing, often called a canard, is designed to carry a substantial portion of the lift, especially at low speeds, while the aft wing contributes more as speed builds. The system is tuned so that the canard, not the aft wing, reaches its limit first. In theory, this prevents a deep, uncommanded stall. In practice, it forces a delicate dance at the bottom of the envelope. When the canard surrenders lift, the nose falls, not as a gentle suggestion, but as a decision already made by the air. On the ground and just above it, this architecture changes the pilot's job in ways that matter at an airport like Compton. The Q-2's engine is mounted up front, so the propeller's wash bathes the canard and amplifies its lift with power. Advance the throttle on the takeoff roll, and the nose wants to lighten early. Reduce power in the flare, and the canard's lift decays abruptly, often faster than a newcomer expects. Add to that a landing gear arrangement built into the tips of the front wing, wide in track but tied directly to a lifting surface, and the airplane can punish rough technique with porpoising, skipping, or an uncommanded yaw if a brake is grabbed or a gust lifts one side of the canard more than the other. Tail dragger dynamics add their own demands. As speed rises and the tailwheel unloads, the airplane's directional stability depends on consistent rudder inputs and careful energy management. Low-speed margins in this design are as much about surface condition as they are about airspeed numbers. The original canard airfoil used on many Q-2s developed a reputation in the home-built community for being sensitive to rain, bug splatter, and even patches of rough paint, which could nudge the canard into its limit earlier than predicted. Pilots learned the hard way that a small degradation in the canard's maximum lift translated into higher rotate and approach speeds and less flare authority when it mattered most. Owners and builders responded with modifications: vortex generators along the canard's leading edge, alternative airfoils, and trim systems that reflex the aft wing's ailerons to adjust pitch balance. But not every aircraft incorporated the changes, and not every pilot had the same experience transitioning between configurations. Numbers tell part of the story. Approach speeds recommended by experienced Q-2 pilots sit notably higher than those of comparably sized factory trainers, with final approaches flown briskly to maintain a buffer above the canard's critical angle. Rotate too early and the forward wing may be asked to do more than physics will allow. Carry the nose too high in the flare, and it can abruptly quit helping, dropping the airplane in from a disconcertingly low height. Crosswinds complicate this further. A slight crab or wing low correction changes the canard's local angle of attack from side to side, and because that surface is forward, any asymmetry shows up quickly as yaw and roll that have to be stopped now, not later. Compton's runways are long enough for light aircraft in normal conditions, but they do not offer the long safety cushions of exurban fields. That compresses the tolerance for second chances if the first attempt starts to unravel. Ground handling reflects the same sensitivities. The Q-2's brakes live out at the canard tips, and the steering workload on a tailwheel airplane is always highest in the first 100 feet of the takeoff roll and the last 100 of the landing. The airplane rewards feet that are active but not panicked. Pilots with time in the type describe the transition as less about muscle memory and more about anticipatory control, nipping deviations early, resisting the urge to chase pitch with large elevator inputs, and using power as a primary tool to modulate the canard's behavior. A misset trim or reflexor can move the entire balance point of the airplane. A few turns of a jack screw may separate a hands-off climb from a nose-heavy lurch that tempts an early rotation. These are not criticisms so much as the operating facts of a specialized machine. They are why the Q-2 attracted devoted builders and experienced hands who valued its efficiency and speed on modest horsepower. But they are also why a routine takeoff or landing could become anything but if airspeed control slipped, if a gust arrived at the wrong moment, or if a small configuration error ate into the already narrow margin below 100 feet. The design amplifies precision and exposes sloppiness, and on a busy urban runway, there is little room to discover which side of that line a pilot is on. Understanding these characteristics is not academic. It frames everything investigators and peers look for after a short, troubled flight. Did the airplane lift off at a sensible speed? Was power reduced unexpectedly? Were there signs of a bounce or porpoise, of a crosswind correction abandoned or overdone? Each clue is filtered through what the tandem wing architecture rewards and what it punishes. With the machine's demands on the table, the next question becomes whether the person at the controls was equipped, by training, recent practice, and intention that day, to meet them. A machine's temperament only matters because a person must live with it, moment to moment. On that January afternoon at Compton, the pilot of N813S approached the flight, as most light aircraft pilots do, with a plan that felt modest and manageable. It was a local departure in visual conditions from a familiar field, the sort of outing that, in ordinary airplanes, functions as a confidence tune-up rather than an exam. There was no tower to negotiate and no weather to unravel. The checklist items, fuel quantity and quality, control continuity, canopy security, trim set, instruments alive, were the kind of rote choreography that marks most general aviation launches. Nothing about the setting insisted that the margin for error was thinner than usual. The airplane did. Investigators routinely begin with paperwork because preparation leaves a paper trail. Certificates and endorsements establish what a pilot is authorized to do. Logbooks say what he or she has actually been doing. For experimental, tailwheel kit planes like the Quickie Q-2, the delta between those 2 points can be decisive. A pilot can be current and legal under federal rules and still be green in type. The Q-2's combination of canard aerodynamics, tailwheel ground handling, and reflexor trim peculiarities means that recent experience is not a generic concept. It is specific to this family of handling qualities. Insurance underwriters and EAA safety counselors have long urged transition training for demanding home builds. But there is a practical obstacle. Very few Q-2s are set up as dual control trainers, and even fewer instructors are current to teach in them. That reality leaves many owners accumulating type time alone, stepwise on quiet mornings, pushing the envelope a knot at a time. People on the field remembered the pilot as methodical, not reckless, and the day's intent as modest. In the absence of a formal flight plan for local VFR flights, intention is reconstructed from routine. A short taxi and run up near the threshold suggests a standard departure. No fuel truck call before startup implies the pilot was satisfied with what was in the tanks. A weight and balance slip, if present in the binder that experimental owners often keep, would show a conservative loading for a solo hop. The most common goals for such flights, hardware confidence after small maintenance, a currency circuit in the pattern, or simply brief exercise of pilot and machine, are all consistent with liftoff, one turn in the pattern, and a return. Each is also consistent with a quiet cabin briefing to oneself. Rotate only when the canard is ready, target a firm, known climb speed, and if something doesn't feel right by a predetermined point on the runway, close the throttle and stop. The Quickie's demands nudge that private briefing into sharper relief. The canard's sensitivity to power and pitch makes trim setting more consequential than in a Cessna trainer. A misset reflexor loads the takeoff roll with a bias that the pilot must overcome or respect. The need for a higher-than-trainer rotation speed to preserve a buffer over the canard's limit changes the go-no-go math. A premature tug is not just inefficient, it risks asking for lift the canard will not provide. A tailwheel's insistence on active feet and anticipation asks the pilot to be fully present from the first yard of the roll, with crosswind technique committed mentally before the throttle opens. None of this is exotic to someone current in the type. To someone reacquainting themselves or adjusting to a change, new tires, a tweak in prop pitch, a different seat cushion, these details can stack up. It is here that intention intersects with risk. A routine local hop is often a pilot's way of managing uncertainty, staying near an airport, staying low in workload, staying ready to abort. But routine can also breed optimism, that a small headwind will materialize on final, that a little extra back pressure will coax the canard along, that a bounce can be caught with a touch of power. The best pilots temper that optimism with rules they write for themselves. Maximum crosswind personal minima, lower than the books. Hard abort points on the runway, verbalize speeds before rolling. Whether those guardrails were consciously in place on this flight is a question investigators try to answer indirectly by reading the preparation in the fingerprints of a cockpit. Trim position at rest, fuel selector detunts, engine run-up notes on a kneeboard. They also look at the recency story in the logbook. When was the last landing in type? The last crosswind? The last short field practice? The point is not to assign character virtues or vices post hoc, but to understand the human calculus in play. In experimental aviation, where a builder's ingenuity meets a pilot's discipline, preparation is part ritual and part engineering, and recency is not a bureaucratic box, but a shield against surprises. On January 21, 2000, the cabin of N813S held one person making those trade-offs in real time, with an airplane that rewards precision and exposes drift. What happened next would be reconstructed from scraps of data and the marks the airplane left behind, a brief chain of events near the runway that would force a hard look at how quickly control can be won or lost. Reconstructing what happened to N8113S began not with a flight recorder, but with people and pieces. Compton has no control tower, so there was no controller's tape to play back. Investigators instead worked from a collage of witness accounts, cockpit remnants, and the story the ground itself could tell. Two instructors in the pattern saw the takeoff. A line technician near the midfield hangars heard the engine note. A pair of students waiting at the hold short line watched the airplane accelerate. Their descriptions were not identical. Eyewitness memories rarely are, but they overlapped in key ways. The Quickie lifted off early, held only a shallow climb, and then veered with a suddenness that suggested the airplane had run out of margin rather than out of horsepower. On the runway, signature marks were brief and telling. There was no long trail of rubber or gouged asphalt to suggest a high-speed runoff. The first obvious scar was a short arc in the infield just beyond the runway edge, followed by a compact debris field where the nose met the ground hard enough to shear the canard and collapse the tailwheel assembly. The wreckage attitude telegraphed a nose-low, right-wing low impact, consistent with a loss of lift at low altitude and an airplane that had begun to roll and yaw away from the center line. Investigators cataloged these orientations, knowing that, at takeoff weights and speeds, small deviations in a Q-2 can compound quickly once the canard's lift starts to ebb. What the engine was doing in those seconds mattered, because a power interruption would point the narrative in a different direction. The propeller blades bore chordwise scratches and leading-edge nicks consistent with rotation at impact rather than a windmilling stop. The spinner showed circumferential damage rather than a single flat crush. The throttle and mixture controls were found forward. There was fuel in the system, and continuity checks through the drivetrain did not reveal a pre-impact brake. None of those findings guarantee full power, but together they reduce the likelihood that the chain began with silence under the cowl. The line technician's recollection of a steady, high-pitched engine note fits that picture. So does the absence of a distress call on the common frequency in the seconds before impact. Inside the cockpit, the clues were subtler. Investigators documented control continuity where they could, mindful that composite airframes shatter differently from aluminum and can obscure linkages. They photographed the trim and reflexor positions for later analysis, knowing that a small missetting could change rotation behavior and flare authority in this design. The seat and harness were intact and latched, suggesting the pilot had not been distracted wrestling with equipment. The instrument faces, airspeed, tack, engine gauges were recorded in place, though frozen needles are not reliable measurements of in-flight values. The absence of a kneeboard note or a marked abort point on a runway diagram is not proof of its absence in the pilot's mind, but it does remind investigators of how much about intention must be inferred. From the statements and the scars, a compressed timeline emerged. The Quickie began its takeoff roll and appeared to lighten onto its wheels earlier than a conservative rotation speed would dictate. Liftoff followed, but the climb was flat, the nose bobbing slightly as if the pilot were guarding angle of attack on the canard. A drift or swerve developed. Witnesses disagreed on whether it began left or right, and a corrective input came. Moments later, the airplane yawed and rolled, the nose dropped, and the right wingtip descended toward the ground. The airplane did not have time or altitude to recover. The entire sequence from brake release to impact likely spanned well under a minute. The critical moments perhaps no more than 5 or 6 heartbeats once the lift picture changed. This portrait aligns with a rapid loss of control near the runway environment rather than a protracted mechanical failure. In a type known for tight low-speed margins, an early rotation or a momentary reduction in power can move the canard past its comfortable angle, producing a mush that invites overcorrection. Add a hint of crosswind or a lapse in rudder discipline, and the aerodynamics can cascade into a roll-yaw couple that requires immediate disciplined inputs. Lower the nose, add power, stop the yaw, that are hard to deliver so near the ground. The absence of a mayday or any extended attempt to re-enter the pattern underscores how swiftly options evaporated. None of these findings absolve the environment of influence. Compton's parallel runways, the short taxi-to-throttle rhythm of a busy Saturday, and the day's light but variable winds impose their own tempo on takeoffs and landings, compressing both time and space to make any miscue more consequential. Understanding how those local factors tighten the noose around N813S is the next step in the analysis. If the sequence was short, the stage on which it unfolded was even tighter. Compton Woodley is an urban island of asphalt and grass threaded between neighborhoods, bounded by streets and roofs that feel close even on an uneventful day. 2 parallel east-west runways run shoulder to shoulder, a layout that moves traffic efficiently but also keeps pilots acutely aware of what's happening off their wingtip. There is no tower to meter departures or issue corrections. Pilots sequence themselves on a shared frequency, listen hard, and make timing decisions on the fly. It's a field that rewards decisiveness. On the day N813S departed, that decisiveness would be measured not in miles but in yards. Runway dimensions matter when margins are slim. Compton's strips are long enough for light aircraft in normal operations, but they are not forgiving of indecision. Shorter than suburban lengths and a narrow visual corridor compress the accelerate stop and accelerate go calculus into a brief window. If a takeoff is going to be rejected, it has to be early. If a rotation is going to be delayed to protect airspeed, it has to be managed without running out of pavement. Narrow runway width also plays tricks on perception, making ground speed appear higher than it is, and tempting an early liftoff. For a tandem-wing kit plane that asks for precise rotate and climb speeds to stay ahead of the canard's limits, those illusions add yet another layer of risk. A slightly too high pitch at a slightly too low speed can turn a clean departure into a low, flat mush that invites overcorrection. Traffic density changes how quickly small deviations become consequential. On weekends, Compton's pattern is a procession of trainers, renters, and based aircraft turning downwind over the neighborhoods, their calls stepping on each other in bursts. Parallel operations mean there is almost always someone else arriving, departing, or taxiing in close proximity. Pilots departing side by side aim to hold their lanes, avoid drift toward the other runway, and keep track of who is where without the scaffolding of controller prompts. A momentary swerve on takeoff, a bounce or a yaw excursion that would be recoverable in isolation becomes freighted with another obligation. Don't cross the center line. Don't encroach on the adjacent stream. That mental guardrail can lead to abrupt rudder or brake inputs just when the airplane is at its most delicate. The weather that afternoon, by all accounts, gave few warnings. Clear skies, good visibility, and light winds are the kind of conditions pilots welcome. But light and variable can be treacherous at the surface, especially at an urban field lined with hangars, fences, and trees that carve the breeze into pockets. A few knots of quartering tailwind, barely enough to stir the windsock, lengthens takeoff roll and eats climb performance disproportionately in a low-power, high-lift-dependent design. Mechanical turbulence down the runway, eddies created by buildings and rows of parked aircraft, can tickle the canard's angle of attack from one wingtip to the other and destabilize a marginal rotation. None of this is dramatic, and that's the point. It doesn't feel like weather until it couples with an airplane near the edge of its low-speed envelope. Airspace architecture adds another squeeze. Compton sits under the descending shelves of Los Angeles International's Class B, a layered ceiling that keeps local traffic low and often encourages tight patterns to stay clear of the big jet corridors. Even without a controller telling you to turn crosswind, the culture of a busy field nudges pilots to make room, climb briskly, turn efficiently, and avoid lingering over the departure end. Noise abatement expectations, written or unwritten, amplify that pressure. The result is a departure profile that leaves little appetite for leisurely acceleration or extended ground effect in an airplane that actually benefits from both. Put together, the environment narrows options and shortens reaction time. A short runway and narrow sight picture invite early rotation. Parallel operations and dense traffic punish drift. Light, shifting winds disrupt lift just when the canard needs consistency. Nearby airspace and community pressures compress climb and turn decisions into the first few hundred feet. In that compact envelope, a misset trim, a slight aft CG, or a small aerodynamic tweak can tilt the balance from stable to unstable. To see whether N813S carried such internal factors into the role, whether its build details, maintenance state, loading, or modifications tightened the vice, investigators turned next to the airplane's paperwork and hardware. The paper trail for an experimental airplane is part biography, part blueprint. After securing the wreckage, investigators asked for the binder most Homebuilt owners keep within reach, a stack of build photos, material invoices, airworthiness forms, operating limitations, and the annual condition inspection sign-offs that substitute for a factory maintenance manual. These records do more than satisfy bureaucratic curiosity. In a kit plane like the Q-2, where no two airframes are truly identical, they map the choices that define how a particular example will behave when it's light on its wheels and close to its stall. The build log shows what the airplane was meant to be. In the Q-2 community that starts with the canard itself, whether the forward wing retained the original GU airfoil, known to be sensitive to contamination and rain, or had been converted to the LS1 profile that many builders adopted to gain a few knots of low-speed margin. Photographs and notes reveal whether vortex generators were added, how the reflexor mechanism was rigged to bias the aft wing's ailerons for pitch trim, and whether the main gear at the canard tips kept the original geometry or was tweaked during finishing. Small decisions, extra layers of glass at a hard point, a different brake caliper, a battery moved aft to offset a heavier propeller hub, carry outsized consequences in this design. Each choice shifts weight and balance or alters control harmony, and the logbook becomes the only place where those shifts are documented coherently. Maintenance entries are the second lens. An experimental's annual condition inspection must be signed by the original builder with a repairman certificate or by an A&P mechanic. The signature alone tells you who has been minding the shop. From there, the details matter. Recent tire changes that might alter toe-in or toe-out on the gear, brake service that could introduce left-right asymmetry, and control cable or pushrod adjustments that change neutral positions. On the engine side, ignition timing, carburetor or fuel injection service, and propeller tweaks all shape takeoff performance. A coarser prop that delivers more cruise speed can sap static thrust on the roll. An idle mixture set lean for smoothness at taxi may hesitate when the throttle is snapped open. Absent a data recorder, these mechanical breadcrumbs anchor or eliminate theories about why a takeoff felt flat or skittish. Weight and balance figures, often treated as a formality in simpler airplanes, are a living variable in a Q-2. The empty weight and moment recorded at certification establish a baseline, but the real story is the range of centers of gravity the airplane can see as fuel burns, and as the owner refines the cockpit over time. Fresh paint, a heavier starter, a new radio stack tucked under the panel, each nudges the numbers. In a canard airplane, those nudges are unforgiving. A forward CG demands more lift from the canard and pushes rotation and approach speeds up. An aft CG reduces stability and can make pitch responses feel springy or delayed. Investigators re-ran the math with the pilot's weight, estimated fuel on board from recovered quantities in the tank and lines, and any baggage discovered in the cockpit. The question wasn't just, was it legal? But what did the canard have to do exactly at rotation? In a design where 5 pounds in the wrong place can steal a knot or two of margin, the arithmetic is operational, not academic. Modifications, formal or informal, round out the picture. Many Q-2s have been updated with LS1 canards and vortex generators. Others remain stock but incorporate custom reflexor ranges, tail wheel springs of varying stiffness, or different wheel and brake packages. A tri-Q conversion to tricycle gear changes takeoff habits completely. A stock tail dragger asks more of the pilot's feet. Propeller selection is its own decision tree. 2-blade versus 3-blade composites, pitch tailored for climb or cruise, each choice visible in part numbers and invoice notes. Investigators photographed the trim tab and reflexor positions as found, counted threads exposed on the jack screw to determine where neutral had been set, and examined control surface hinge lines for witness marks that indicate rigging bias. None of these are smoking guns alone. Together, they define the envelope the pilot had available when the throttle went forward. What emerges from the paperwork and hardware is not a mystery solved, but a frame narrowed. If the canard profile was the older, more sensitive one, if the reflexor was set a notch nose up, if the propeller favored cruise, and if the CG sat near the aft limit with solo pilot and low fuel, then a short urban runway with light variable winds becomes a sterner test. Conversely, if the airplane carried the later aerodynamic improvements, a climb-biased prop, and a conservative CG, then attention turns harder to technique and timing. In experimental aviation, the airplane you flew yesterday is the one you built, maintained, and configured today. With the mechanical and mathematical context established, the analysis circles back to the person in the seat. Preparation, currency, and type, and the split-second choices a pilot makes when an airplane feels a touch light or a touch slow often decide whether a marginal moment passes unnoticed or cascades. The pressures and habits that shape those choices are the last, human dimension of the story. With the mechanical footprint established, the inquiry turned to the human one. Rules and numbers describe what an airplane can do. Habits, recency, and judgment decide what it will do on a given day. In experimental aviation, this distinction is stark. There is no factory syllabus for a Quickie Q-2, no line of dual-control trainers for checkout flights. Transition training tends to be informal and opportunistic. Ground coaching from another owner, a few supervised high-speed taxis, then solo circuits on a quiet morning. Insurance companies and the Experimental Aircraft Association have long urged structured transitions for demanding homebuilds. But with the Q-2, the supply of mentors and machines is thin. That scarcity makes currency and type less a matter of calendar days and more a fragile set of muscle memories that dull quickly when not exercised. Investigators looking at N813S were not searching for a moral failing. They were testing whether the pilot's recent experience matched the airplane's demands. Federal currency rules are a coarse filter: 3 takeoffs and landings in 90 days to carry passengers, a tailwheel endorsement somewhere back in the log, but proficiency is narrower. In a tandem wing tail dragger with a canard that quits first, Recency means remembering how much pitch to ask for and when, how to let speed build in ground effect without a creeping drift, and how to correct yaw with rudder early rather than with brakes late. It also means having practiced aborts and balked rotations until they are automatic. These are skills that atrophy quietly, especially in pilots who also fly forgiving factory types, where the wing warns, the stall breaks cleanly, and a bounce can be ridden out with modest corrections. Pressure at a non-towered, busy field is subtler than a hard departure time. It's the social tempo of airplanes in motion. On a mild, clear afternoon with radio calls stepping on each other, a pilot rolling onto the runway feels the tacit nudge to keep it moving, to make a prompt rotation, to climb briskly, to fit into the flow without delay. Planned continuation bias can slip into that space. Once the throttle is open and the airplane feels light, aborting a takeoff demands an act of will that runs against momentum and against expectations. If the nose starts to bob in a low-energy mush, or the airplane begins to drift toward a parallel runway, the mind often frames it as a small problem to be solved in the next second, rather than a reason to close the throttle now. That cognitive lean is not negligence. It is a human pattern observed in accident narratives across categories. The moment when a marginal liftoff turns into a true upset is where decision-making speed becomes decisive. Startle compresses thought. A sudden yaw or a wing drop near the ground narrows attention to the horizon and the center line and invites large, symmetrical control inputs, a pull to arrest the sink, aileron into the low wing, that are exactly wrong when the canard is near its limit. The correct response is nuanced and counterintuitive. Lower the nose to regain energy. Add power smoothly, without overboosting the lift on the forward wing. Stop the yaw with rudder and avoid any brake. In a Q-2, those steps have to be sequenced in heartbeats. They are easier to produce if they've been rehearsed, mentally or in recent flights, because rehearsal acts as a shield against startle. There's also the problem of cues. Light and variable surface winds rarely feel like weather, yet they change the aircraft's story through a pilot's senses. Acceleration that feels a little soft, a windsock that lifts and sags, a crosswind correction that seems to require more foot than expected. Each is a small clue that the margin is thinner than planned. Recognizing those clues as cues to slow down the sequence or to reject the takeoff is a learned behavior. So is ignoring illusions baked into the airport itself. The narrower than usual runway at Compton that makes speed feel higher than it is. The adjacent traffic that magnifies the penalty for drift and nudges a pilot to correct sharply. The airspace culture that favors early turns and quick climbs. None of these factors determine an outcome by themselves. They frame how choices feel in the cockpit. If the Q-2's design exposes sloppiness, it also rewards discipline. Pilots current in the type speak of personal guardrails, stating rotate and abort speeds allowed, marking a hard stop point on the runway during taxi, adding an extra knot or two for light quartering tailwinds, promising themselves that a bounce becomes a go-around without argument. These are the small decisions made in calm moments that govern the big decisions made in turbulent ones. Whether such habits were fresh and accessible in the minutes before N813S rolled is something no paper can prove. But the pattern of events, a brief, flat climb, a yaw and roll near the runway, no time for recovery, matches the footprint of a human system working at the edge of its recent practice. In the end, the same matrix that defines most small airplane accidents emerges here. A demanding aircraft at the bottom of its envelope, a busy urban runway that compresses time and space, a pilot making split-second choices while skills that matter most depend on recency in that exact machine. Hardware and environment set the stage. Cognition and habit determine how the scene plays out. With those threads gathered, the last task is to stitch them into findings. What the rulebook says, what the evidence supports, and what lessons endure when an airplane like N813S does not get a second chance.